Samuele will be presenting multi-channel target speaker extraction with refinement, which is a submission from the WAVLAB submission for the second Clarity Enhancement Challenge.
Yeah. Okay. Can you see my screen?
Yeah, we can see you and hear you and see the screen. Okay,
cool. Hello everyone. I want firstly to thank you all the organizer and of this challenge for their work. It's a very interesting project and challenge. I'm Samuele and I'm a PhD student at the Università Politecnica delle Marche, Italy, and I'm going to present our submission to this challenge. So we mainly developed this system while we were at Carnegie Mellon University at Shinji Watanabe's lab. So that's why I'm using their slide template. In this presentation, we'll briefly explain some problems we have to overcome towards the challenge. Then I give an overview of our submission, which builds mainly on previous work from Zhong-Qiu. And following, I will show some results we obtained on development set and let you hear some audio samples. And finally, I will talk about some weaknesses of our system and possible future work. So this challenge, in my opinion, is the most difficult data set, at least the synthetic data set ever encountered. Like it's, I would say that the difficulty-wise, signal-wise, is on par with the Chime 5.6, but Chime 5.6 is a real-world scenario with multiple arrays. And for example, the scaling variant SDR on development set of the anechoic target versus the mixture is around -12 in average. And this, for example, on WAMR dataset is -6. Wall Street Journal 0 to mix is 0. So very challenging. And some mixture require actually superhuman ability because the SI-SDR is very, very low. So on top of this, we need to do speech separation because we can have multiple speakers. We can do, we have to do the noising. We have to remove noise because there could be, the interferer could be noise, and plus the reverberation ideally to get the possible best oracle target signal. This with pretty severe latency constraint. But we have some advantages. One is there is no computational requirements on the algorithmic latency. So that is a big advantage, I would say. And also we have a prior information on the target speaker. It always starts afterwards the interferer if there are other speakers. So for example, before it was asked a question on how a DNN can learn to isolate the target speaker. If you train it on the data, it will always learn to enhance the last speaker and treat the ones that talk first as interferers. So you don't need the permutation invariant training. This speed ups trainings quite a bit and also makes it very simple. So in theory, you don't even need enrollment, I would say. But we use that on our system. Enhancement alone is not enough. Like with Oracle enhancement, you calculate ASPI, of course, it's 0.7 almost on the development set. So you need both listener compensation and enhancement. Also, listener compensation is not, the fitting is not, alone is not enough because the baseline does only fitting plus dynamic range compression. And the results are, I mean, for the baseline are quite low for ASPI. So you need both. And we built our system based on our previous work, which was on the L3DS ICASP challenge this year. This was much simpler because you had only to do the noising plus the reverberation, so no interference speakers. There was no latency constraint, so it was all non-causal. And what we found out was that what worked best is using complex spectral mapping and a strong DNN. So complex spectral mapping, basically we treat the complex STFT of the multi-channel input as an image. So you have an image which is frames times frequency times 2 channels for real imaginary times the number of microphones. And then you try to reconstruct the target speaker oracle anechoic speech. And that was pretty effective. Like using a strong DNN, which was based on UNet, we got a very high improvement in this challenge with respect to many state-of-the-art models like DMAX or CompTasnet or Fastnet. And another thing we did was iterative enhancement. So we trained the two DNNs, both with complex spectral mapping. So both were UNet based. And you train the first DNN, you get to get an estimate of the anechoic target speech. And then you freeze this first DNN and you use it to compute a multi-frame multi-channel linear filter. And then you train a second DNN, which takes in output both the original multi-channel mixture plus the enhanced speech from DNN1 plus the output of the multi-channel linear filter. And that improves quite a lot using both of the two DNNs. And plus you can do iterative, you can run the DNN2 iteratively with the beamformer. And that improves a little bit the order rate in that challenge, but not much the signal-based measure, so such as toy. So here we extended this framework. We had the possibility of using speaker embedding, and thus we use that, and we moved to a target speaker scenario where the two DNNs are conditioned with the speaker embedding based on enrollment patterns. Then we had a beamformer, and we also used the STFT based listener compensation. So we moved from our UNet style DNNs to recent proposed method, which is a TF GridNet. That is the main the thing that brings most of the improvement. It has been shown into recent work to give state-of-the-art performance both in anechoic separation, but also in noise reverberant separation. And we adapted this model to use the target speaker embedding from the enrollment utterance by basically plugging into the model on each block film layer for conditioning. And also we made it causal, like we swapped the layer, instead of global layer norm, we use layer norm, and then we use causal self-attention. We use in the subband temporal module unidirectional RNN. And also we, like the previous presentation, we basically use for the prediction of the STFT frames for the synthesis, so we can reduce the latency. Like we use 32 kilohertz. We have 16 milliseconds analysis windows, 4 milliseconds strides, and that should give a 60 millisecond latency. And what we do is predict also the current plus the 3 future frames. So the latency is reduced to only one up size. And also we use causal beamforming. Okay, this is very simple. It's a vanilla multi-channel linear filter with exponential moving average and 0.5 forgetting factor, because we know that the listener head can actually always rotate. For the enrollment DNN, we didn't use a causal network because it's not needed. Like you usually can you can do it offline at enrollment, and it's a smaller TCN dense net. Well, we didn't use TF GridNet because it wasn't needed. Like this was much faster to run, and TF GridNet has RNNs and attention, and it's quite heavy on the computation, even if the algorithmic latency is quite low. So basically, all these operations are performed in the STFT domain, and so we moved the equalization and the dynamic compression in STFT domain. That was pretty trivial. It's nothing fancy, like we did a multiplication. This is the equalization is a multiplication in STFT, and we used a very small number of taps to avoid artifacts. Dynamic range compression, we do dynamic range compression for each time frequency bin, but it was very simple. It's taken from a paper, and both are slightly inferior in terms of ASPI. Like we lose a bit of ASPI when we feed the oracle signal, but it's not a big deal. Like we counted more on the enhanced signal. And how do we train this network? We first train DNN1 and DNN speaker. So the speaker for the DNN for the speaker embedding. And we use a loss function based on magnitude and L1 loss on the waveform level. So we train DNN1 and DNN speaker first. Then we train DNN2, keeping the first two freezed and giving to it the output of the beamformer and then DNN1. And then as the first step, we just fine-tune DNN2 with the same loss, so waveform plus magnitude of the estimated signal after equalization with respect to the oracle signal after the equalization. So we don't use ASPI like for fine-tuning the system, also because we found that ASPI is sensitive to scaling. Like if you amplify to plus infinity your signal, ASPI goes up. So you don't want to do that with DNNs because they will cheat. And so we found on the development set that basically using conventional techniques like MVDR, because in some examples the SI SDR is very, very low, it doesn't really help. The new INUB with the TF GridNet, it outperforms the non-causal one we submit to a L3DS challenge. So casual system with very strong DNN beats, in this case, a non-causal system with also strong DNN, but less strong. And adding a second DNN plus using the fine-tuning strategy helps quite a lot in the ASPI. Like there is a big advantage here. And also using external data, we tried to use external data from LibriVox with much speaker diversity. It didn't help that much. So maybe it was our fault how we generated that data. So let's listen to some examples. Here is the mixed.
Navigate the talk or text within system. So taking the district line is an easier route from West Kensington.
It's difficult to hear the target speaker.
Did you pull the curtain in front of you?
So like it's something between here.
Navigate the talk or text within system. So taking the district line is an easier route from West Kensington.
It's almost impossible. I can hear a bit with my headphones actually. This is estimated speech from DNN1.
Did you pull the curtain in front of you?
So there are some artifacts, and this is after DNN2.
Did you pull the curtain in front of you?
So much less artifacts, I would say.
Did you pull the curtain in front of you?
Yeah, this is the oracle. So it's pretty close to the oracle. Okay, sorry. So future direction is okay. The GridNet works very good. The algorithmic latency is respected of the challenge, but it's quite high on the computational side. So future work should go in this direction to use quantization, compression, pruning, or distillation, and try to make it lighter. And also an issue I found that here is not reflected in this challenge is generalization to real-world data. I tried to apply this model to Chime 5.6. It doesn't work at all. So like even if I change it to reflect that scenario, it's quite tricky to get it to work. So one direction could be like try to leverage semi-supervised methods. There are a couple out there that can be tried out of the box. And we didn't try different speaker embeddings because they weren't allowed in the challenge. But one maybe can use WAVLAB or Expector embeddings for the speaker and maybe improve the performance. And iterative processing does not help in our case. So we observed in the 3DS, it only improves the order rate. We try to do it also here. But if you try to, after DNN2 enhancement, you try to run DNN2 iteratively, the performance gain is not worth the, like you gain very little in terms of ASPI. It's not worth the additional processing. So maybe because the DNN is too strong. So with the lighter DNN, maybe it could help the iterative processing. And yeah, thank you for your attention. And if you have any questions, I would be happy to answer them. And also, yeah, reach out to my email or Zhong-Qiu email.
Well, thank you very much. Very interesting. We've got a couple of questions that have come in straight off. Firstly, what is the model size in total, and what's the sort of the computational load?
Yeah, the model size. I don't remember. It is it's several millions. It's I mean, it's not something that you can run on an embedded device for sure.
Right. Okay.
So that I can answer you. Like even for training, you need quite big GPU, like at least 24 gigabytes.
Right. Okay. So that, I mean, that goes some way to answer that question.
Yeah, it's I mean,
Trevor has a question. Written it down, but you've also put your hand up, so I may as well just let you ask it yourself.
Yeah, I thought I might go live. So you talked about the problem of generalizing to the Chime data set. Do you have any sense of what is preventing the generalization?
Yeah, there are multiple things that I think. One is my simulation is very crude. So like, for example, on Chime, you have Kinect devices, and I don't have any way to simulate real arrays. Like in my case, there are virtual microphones with hypercardioid, very crude hypercardioid directionality, but there is no real transfer function of the array. In your cases, you use for example, on Clarity, you use the add transfer function. So it's more realistic, the simulation. But on real world data, like it's that could be tricky. Could be tricky also the fact that people move and people place things in front of your array, in front of a microphone of the array. They can be very close to the array, for example. They can be very far in another room. So it's pretty challenging, that scenario. But it's also very different from I would say this one.
We have another question here from Elijah Ma. If you want to go ahead.
Yeah, here. Can you hear me?
Yes.
Oh, cool. Yeah, so I'm quite interested about your NeoR module. So you mentioned that you find something about the NeoR, and could you talk a little bit about how do you train on that? Because my understanding is that NeoR is just amplify the signal, right?
Yeah, right. It's an equalization. You basically run your TNN, right? You get the estimate, and you feed the speaker audiogram, whatever speaker, you sample randomly speakers audiograms, you feed it, and you obtain an equalized version of your enhanced signal. And you do the same for the Oracle anechoic target signal, and then I compute this loss. So basically the loss compensates for, takes into account the linear equalization you do. So it can boost some frequencies, and mainly help, for example, on in cases where you can have artifacts, for example, in some cases, I would say.
Oh, so like yeah. Sorry. So do you train that part separately, or do you train with the neural network?
I backpropagate through it. So yes, I train everything without accounting for the fitting, the equalization. And then at the very end, I fine tune the NN2 output with this strategy a bit. Like for even one epoch gives pretty good results. So it's a way to make the DNN to take into account the operation you do afterwards. In this case, simple linear equalization. I don't have much experience on fitting rules and things like that. So we decided to go for the simplest thing possible. And I mean, if your enhancement is pretty good, I would say it kind of works. Also because Manuel Pariente, one of my colleagues here, a coder, told that maybe people with hearing loss could take time to adjust to complex fitting rules. So we decided to go to something very simple.
Okay.
And yeah. I tried actually the fitting rule from previous challenge edition, and it was worse actually than using this pipeline of linear equalization plus dynamic range compression, at least on the anechoic target signal.
Okay, cool. Thank you.
Okay.
Will's muted, I think.
Yeah, I was just saying, John, you've got your hand up.
Thanks. Yeah, brilliant. I'm just struck by your system. I mean, when you go down to right down to minus 11 dB, you're still getting story scores of kind of 0.9, which seems quite remarkable. And I was just wondering, yeah, there must be some scenes where your story scores are not kind of above 0.9. And if you looked at the scenes where it's doing poorly, can you learn anything by places where it actually fails? Have you done anything?
I think what we observed and why we tried to add external data is that the loss for the second DNN, okay, the first DNN took quite a lot to train, like 30 epochs, to go into convergence and reasonable performance. The second DNN is very fast to train, but it at around minus 17 dB improvement, it basically flattened out. And we tried to use external data, because in the very, very complex low SNR scenarios, you can hear some artifacts, you can still hear some artifacts. It didn't work. So we thought at first that it was a problem of speaker diversity. It doesn't seem so. So maybe, and in those new scenes, we just swap the speakers. So the noise are the same, and the reverberation are the same. We use the same toolkit as of the official challenge. So one thing one can do to improve those edge cases where it's superhuman ability at this point is like maybe try to generate more scenes with different, also different noises and loss clipping. You want to clip the loss to make the DNN focus on the art examples at that point. That could be improved a bit, the pair. But at this point, I would say it's more like playing with the model, like small adjustment. It's the real issue is the generalization to real world data plus the reducing the computation.
Right. So in the challenge, we kind of made the data difficult artificially by kind of going to these extreme SNRs where people wouldn't be holding conversations properly if they're hearing impaired. I mean, I think we would like to have made it difficult by making more variability in the data. So what was it in the data which you would say was a thing you were able to latch onto, which made
I mean, the enrollment, I don't think it improves a bit. It improved a bit, but I have to make more ablation studies. I'm not quite sure. Like, because the DNN can still learn that the last speaker is the right one, for example. But at the end, you need, I would say in the real system, you would definitely need something to tell to your system that which is the right speaker to enhance, no, for example. So either it could be the ordering, or could be, I don't know, like looping direction, or some features from, I don't know, like a face tracking, something like, or eye tracking, something like that.
Yeah, I guess the other big difference between the chime and this is there's kind of very clear red speech, where chime is kind of quite incoherent conversational speech.
Yes.
So that would be a factor, I presume.
Also.
Yeah. Okay. Thanks.
Well, unless there's any other questions, I think we're just slightly over the time that we posted.
Okay.
Thank you to everyone who took part in the session. Some very interesting papers and some really good results. I think next we've got a 20-minute break before the